time. So if you have a routine to get the time, to get your PHC value, you can run this application. I listed here also the cross timestamp, but it needs to be supported in your hardware. So having only get time, you can run this application and see how your system time is synchronized to the PHC. And for the PTP4L, we need to also have a method to discipline the clock. Because as I mentioned before, we want to discipline the follower clock to the master, to the leader. And we need to have also a method for generating and reading the TX and RX timestamp. Linux PTP. Let's talk about the Netdevsim. What exactly is that and why we choose this one? So first of all, this is the simulated networking device. So it's possible to test the kernel API using this simulated networking device because you can create a device and you don't need to have a hardware support for using the kernel API. So for PTP, as I mentioned before, you need to have a hardware clock, you need to have a timestamp possibilities and so on. And in the Netdevsim, you don't need all those stuff. You can just run the PTP APIs without having any hardware support. And having different hardware offloads enables the possibility that in the software, your application will see if the hardware is available once in fact it's not. So with Netdevsim, you can enable all the Linux PTP applications without any access to the PTP capable hardware. And the last thing that was very important for us in our implementation was the fact that there is implemented packet forwarding between instances. So to pass the traffic in Netdevsim, you need to put the devices into namespaces. And thanks to that, you can pass the PTP traffic, so you can enable any PTP action in the PTP files, for example. And now let's talk about the different driver that is very important for this talk, that is the PHC mock. The PHC mock emulates the PHC for the virtual device. If you are talking about virtual devices, we can think about it like in Netdevsim. So we have the Netdevsim device, and we have PTP mock that is capable of creating the PHC for Netdevsim devices. And we have also one important thing here, that PTP mock is taking the clock monotonic row, and it adds the mathematical overlay over that. So you can have the returned time in UTC, TIE, or whatever time zone you need. And it is possible to timestamp time counter subsystems that are implemented in this driver. So what you can do with this PTP mock, it creates a PHC for you, and it allows you to set the virtual time. And of course, at this virtual time, you can read it. And you can also make all those things that are required for disciplining the clock, so changing the virtual frequency and so on. And on this picture, you see the routines that are implemented via PHC mock. And this API is pretty similar to the kernel API for the PTP control that we presented and Maciek presented in the previous presentation. As you can see, again, we need to provide a method for adjusting the frequency, the time, setting the time. And on the bottom of this picture, we have also those routines for this mathematical overlay over the clock monotonic row that it's used for getting the time in this module. So how you can test the PHC driver if you are using it? First of all, you can set the value. Then, of course, you can try to read this value and make some frequency adjust to make sure that all operations are done correctly. And the example that I'm very frequently using in my everyday work at Intel is this one. I'm using it on real hardware, but it's very useful also here in the Netdevsim implementation. Because what this routine really does, sets the time to 0, makes the frequency adjustment by the unit of this one is the parts per billion. So we are increasing the frequency per 10 per second, 10%. 10% of 10 is 1. So after this routine, you should see that the result that it's more or less 11 seconds. And if the result of this function is more or less 11 seconds, then you can make sure that the access to your PHC is correct, and you can modify the clock. What is important, maybe not in the case for the Netdevsim, but in our everyday work with the hardware, is that for any PTP adjustment, sometimes you need to also do the same on the file level. And having this routine allows you to verify if the file modifications are working also correctly.
Okay, so after the last Netdev, we started thinking, how can we actually implement all of this? And starting to research what is already there, what's missing, and how to tackle the problem of getting an emulation of timestamping. So at the beginning, we found that there is a PTP mock. Well, actually, I initially implemented my own device, but then looked into the kernel, and the PTP mock was upstream to that just at the same time. So, okay, we have a hardware clock. Okay, that's one tick on our checklist. The second one was the driver for the hardware clock. So this is our point of reference. This is what allows us to control and overlay over the clock monotonic row counter of the CPU. And actually, this creates our PHC that we will use later on as our virtual hardware clock. The next step, obviously, we need some networking interface. So our NIC driver, as Milena said, is the Netdevsim. So we needed to check what's there, what's not there. Since the actually it's David's fault, because he pointed out to the fact that the support for passing the traffic between two Netdevsims was just upstream. So we started looking in there and found out that okay, we have those sticks on our checklist. What else do we need? So to get full timestamping support, we obviously need also means of getting the timestamps for the transmit and receive, and the support for all the laundry work that's needed to be done behind the scene to enable the offload. So that was the missing piece in the Netdevsim, and that's what we needed to implement. So we have the hardware clock, we can forward packets, what we connect them, and actually mock up the timestamping. So obviously, I'm an architect, so I took a piece of paper and started like scratching something. So this is what we have. We have a clock monotonic row, we have the time counter translation, we have the PHC clock on top of it. We have the link to the relevant PTP mock, so our Netdevsim can point towards this PHC mock. But obviously, that was not all that we need. So we first needed to also implement the way back. So we needed to implement somehow a connection the other way around, so that we can actually get the time from this PTP mock. It was actually not exported as a functionality, so we weren't able to just use the get time to get the time from this PHC mock. Then we obviously needed to somehow mock up the receive timestamps, mock up the transmit timestamps, API, implement the APIs for the Ethtool so that the PTP4L can understand that we actually can do timestamping as well, not only find the PTP clock that is attached to our device, but also understand that it can do hardware timestamping. And we needed to get the set and get timestamping modes IO calls supported. So this is a quick reminder of how 1588 works. So it's based the very basic implementation, most basic one of the two-step timestamping is based on the sending the sync message with the follow-up message. This is the sync message is generated by the time transmitter. So in old nomenclature, that was the master. Now with the 1588 positive time transmitter. So it will generate the sync message, which will get timestamp on both ends. So this will be our transmit timestamp on the time transmitter and the receive timestamp on the receiver. Then there will be a follow-up message that will contain the Q1 timestamp that's connected to the sync message. And to get the path delay, we will also obviously need to request the delay request and get the delay response. And in this case, this will be our transmit timestamp from the time receiver, and this will be our receive timestamp on the time transmitter side.
Okay, I'm not an architect, but I also prepared a drawing to show the flow. So this is our flow in which we implement the PTP implementation in the Netdevsim. So as you can see, we have like two PTP for applications. We have two namespaces marked here as NS1 and NS2. And what exactly is that? When the PTP for L is running, it opens a socket. It marks in that we want to have a timestamp request. And from the driver perspective, we have the escape. When we are processing the packet and we see that there is a timestamp request, we are setting appropriate value in the SKB that Maciek showed on the previous presentation. And right now, it's the time for getting the timestamp. And how we are doing that in the Netdevsim implementation. So I am getting the value of my PHC mock. That will be the timestamp value for my application, for my PTP4L. And this value will be the TX timestamp. And also I need the RX timestamp, right? So I'm getting the value of the PHC mock2, which is my peer PHC, and provide it back to the Netdevsim one. The next happens a little trick that we are doing in the implementation, but we are doing the forward SKB with the RX timestamp to the network stack on the peer side, and we are cloning the SKB. We are cloning the SKB because when we are doing forward, then the Netdevsim one loses the access to this SKB, and we need to still provide the timestamp back to the stack and then to the PTP application through the error queue. So you will see it later on the implementation how exactly this is done, but this is the flow for now. And we are providing back the TX timestamp value to the network stack and then to the application, and same on the RX side. So having all those, we have a fully functional TX and RX timestamping, so you can enable the PTP4 application as long as you have the method for controlling and disciplining your clock that we implement on the PHC mock. So let's go through this step by step what we are doing in the Netdevsim driver to provide PTP solution. So first of all, right now there is no connection between the PHC and the Netdev device. So what we exactly need is that we need this PTP info structure that is a part of this huge struct that we presented some time ago, and we need it to access all the APIs, the get time, set time functions, the adjustments that we need requires this PTP info. So we had to expose it in the PHC mock, and this export can be then used in the Netdevsim driver. So I mentioned right now the Netdevsim exposes the PHC. So if you make a ETH tool on the Netdevsim device, you will see the PTP clock number, but it's not accessible, in fact, so you cannot read the time, set the time, and do any specific action for now. So as I mentioned, what we added in the code, we are exposing this PHC infrastructure, this whole structure with all the PTP capabilities, and we implemented some fallbacks to those functions. So we have a connection to our PHC. What else we need? We need to have a method for configuring the timestamp. So we can set and get the timestamp configuration. We can also disable and enable RX and TX timestamping. And we need to set some timestamp filters. In fact, in our implementation, it's done in a way that all the RX filters are fallback to the filter all, because we do not differentiate any specific type of the packet for the timestamping. We are doing Rx timestamps on all. And this is pretty compatible with all the kernel flows. That's what we have also at Intel drivers, and I think NVIDIA's also. So this is the functions that you need to implement, for example, in your driver if you want to enable PTP. So you need to have a method for getting and setting the TS config. And as I mentioned, on the right side of the slide, you have the set TS config method. At the bottom of the slide, you have the Rx. You have a lot of filters here, but at the end of the day, they're all transmitted. There's a fallback for the hardware timestamp filter all. And this is how it works also with the Linux PTP with Linux PTP application. So then we connected these functions with some Netdev ops. And let's go to the TX timestamping, because this part is usually much more complicated when you're implementing the PTP solution. So as I mentioned before on this drawing when we showed the design, our TX timestamp value is our PHC time taken from the PHC mock. So we have the PHC allocated by the Netdev, and we are getting the timestamp from this PHC to return back to the stack. We are doing it only when the timestamp is enabled. And we need to keep the original SKB, return the timestamp back to the stack. As I mentioned before, when we are doing this forward, we are losing the access to the SKB. So we are making a copy of our SKB to make sure that timestamp can be provided back to the stack. And using this routine, we can provide a timestamp value back to the stack and then to the application through the error queue. And after all those actions, we are ready to release our TX SKB. How does it look from the code perspective? As you can see, if we want to do a timestamp, we are getting the access to the PHC info structure. Then we are reading the value from the PHC. And it's in the line when we are doing the get time. Then we are doing this SKB copy that is required for providing back the TX timestamp value, as I mentioned. We are setting information that the timestamp is in progress. This is done to make sure that the stack will wait for this TX timestamp instead of, for example, returning some software timestamp instead. Then we are doing this forward to our peer, and at the end of the day, we are ready to provide the timestamp value back to the stack and to free our SKB. Now let's talk about the Rx timestamping. The situation is pretty simple here because what we are doing, we are getting the time from the peer PHC. And after that, we are forwarding a copy of the SKB to our peer, to our other site. So how does it look in the code? Pretty simple. Again, get time. But in this specific case, we are getting the time from the peer. And the Netdevsim implementations provide you in your Netdev, you have an access to the peer. So it is really doable. Now let's talk about the Ethtool, because what you need to do to enable PTP solution in your driver, you need to also enable some Ethtool in the Ethtool. And as you can see, we are providing here some TX and Rx filters. And what was done before we did our implementation was the exposition of the PHC index. But as I mentioned before, the index was exposed, but no specific action could be done on this PHC. And this is how it looked like on the Netdevsim device. So as you can see, your I wanted to say hardware, but it's your simulation is fully capable of doing timestamping and PTP hardware clock. And this is the index in this specific case is 0. And you're able to do the TX and Rx timestamping. So you are able to run the PTP for our application.
Okay, so now how can we actually run some PTP4L on what the small Frankenstein that we designed? Current limitation or more like design choice of Netdevsim is that if they are connected, they require to be put into separate namespaces. So obviously we also need to run PTP file in those namespaces. I'm a lazy architect, so I just reused the script that originally came with the patches to create this connection. So basically what they do is they create two namespaces. One is called NSSV and the other is called NSL. It creates two Netdev, puts them into those namespaces and connects them together. So everything else was not needed, so I just commented it out from the script. So no cleanup, no sending traffic through those and so on and so forth, because, well, we don't need it. Good one. Yeah, so unfortunately, this solution obviously had some limitations. The timestamp quality is not great because unfortunately we try to capture one timestamp on one device, so it gets the monotonic row, translates it through the PHC implementation of one clock, and it gets the clock monotonic row on the other end, so from the peer device, then it translates it through its PHC clock, and then put those two together as one is the transmit timestamp, the other is receive timestamp. So unfortunately, we don't capture them both at the same time, or on that later. So this results in the master offset being like revolving all the way around a couple hundred to a couple thousand of nanoseconds, depending on the system loads. Obviously, once you load the system, the offset gets better because your CPU doesn't go to sleep and don't have time to rest and sleep and decrease the quality of your monotonic row timestamps. So the traffic, yeah, as I said, mentioned, is only assigned passed when we are assigned to namespaces. So basically, if we run the PTP4L inside our namespace, this is for the client part. Give it just regular commands. It doesn't need any EX transmit timeout flags or anything like that because fortunately we do this fast enough. And then it will start, but you can see that it more or less syncs. The problem is the path delay. As I mentioned, the path delay in this case is the difference between two timestamps capture points. So they are not tied together. They are loosely taken, and depending on what kernel also does in this time, they will either be close together or not really. So that unfortunately breaks the quality of the synchronization, but it's still time for what we wanted. So the use cases, why we actually did that. The first and most important part was to actually show you how that it's not that complicated to implement it and show you some way around. But also we wanted something to play along if we don't have the access to the hardware. So now I can just take my laptop, put the Netdevsims together and still be able to develop something while I'm flying somewhere over the ocean. We wanted to, yeah, just like I said, enable Linux PTP development without the access to the hardware that actually can do the timestamping. You can also do some debugging, obviously, and you can actually show what APIs are used for the most basic scenario. Obviously, we don't do the magical enable function that does it all for hardware pins because we don't have any hardware pins so far. Maybe we will mock it up later, but we will see. And for maybe someone will be brave enough to put some self-tests to the kernel. We for now didn't tackle that problem, but that's also a possibility. So next steps, obviously, we will try to upstream this. Hopefully it will pass the filters. It's not, and also there is a catch because actually the latest version in the release candidate of 6.10 kernel, the Netdevsim implemented, I believe, NAPI polling or something along those lines. And unfortunately, it broke passing the traffic between two Netdevsim devices for me. I tried it on a couple different platforms and it didn't work. So I don't know if it will be free. I don't recall, but there was something along those lines that was implemented, and unfortunately, this broke both tests for me and passing the traffic on the platforms that I tested. So there may be, you may need to revert to the tree from and to stay with this feature unless the Netdevsim gets corrected. That's not enough. So the next step would be to improve the timestamp quality. Actually, the time counter API and cycle counter that is used by the PTP mock can do the trick of converting a raw value of the counter through the conversion that the time counter applies to the regular timestamps. So technically, it should be possible to actually get one sample of clock monotonic row and pass it through two different implementation of PHC clocks. And convert that using the cycle to nanosecond function and get the timestamps that will be seen by those two devices of the same point in time. This should fix the problem of weird offsets that result from different path delays. So the different points that those timestamps were captured. So if it works, it will need a bit more exposure of PHC and mixing the APIs of the PTP mocks into the Netdevsim. It will be a bit uglier solution, but may provide better results. So if there is interest in getting better synchronization, we will go this way and also improve this solution. And yeah, now I will also sit back and enjoy the demo. We didn't want to play with live demo gas, so I will just mock it as well. So we run Tmax to run to commands, well, on the server side and on the client side. If you actually are curious how it works, then the best master clock algorithm kicks in and takes the clock that has a lower MAC address because we are not specifying any clock class or anything special in the PTP4L call. And as you can see, the client side starts synchronizing and it gets to this area of couple hundred or a couple thousand microseconds, nanoseconds. Summarizing the talk, exit. So yeah, thank you. Now the floor is open for some questions if you're curious about more.
Thanks for the presentation. I had some basic questions. Two, maybe I'll start with. One is anyone working on non-ioctl based for the PTP mechanisms like through Netlink?
No, this is because it's currently done exposed through the POSIX clock API, so it's completely different subsystem. It would require rework there first.
And the other one I wanted to ask was, is there gotchas or advice that you give to people trying to implement hardware for this? Like, a large part of this is the hardware that does the PTP work. Is there things that you would give as gotchas or mistakes that you notice people are making all the time, either in the software or in the hardware?
Gotchas. I don't have any list like that. The gotchas are read through the right manual and implement the right things in right places. This is the biggest gotcha, but I hope this one will be easier after the previous presentation. other than that, yeah, the important part is that you need to keep the reference of your SKB that you for the transmit timestamp. You still need to keep this SKB, and you need to set the flag so that the stack doesn't think that you don't support hardware timestamping and just returns the software timestamp. So those are the biggest one, I think. Just like the other path. Yeah. Others, no.
So one thing that I didn't see in talk before in this one is how all of this integrates in with PTP.
It does not. It's a separate subsystem, but my talk on your workshop will actually somehow try to tie it together, maybe, because there is now currently no connection between those two subsystems. Like a strict, you can, for example, the DPLL that's your PTP block or something like that.
Not paying attention to it, I thought it was trying to make common code out of what all the drivers were having to do.
No, it's a different subsystem.
Okay. Okay. And then one of the requirements you said was syncing from clock to the PHC.
Yeah, this is a whole big story and stock worth of its own. I tackled it a bit on the last Netdev because yeah, the problem is that our devices live somewhere far away ahead, like behind the PCIe bus. The PCIe bus is not meant to be like for time critical operations. So when you send the request to get the time, it is somewhere scheduled on the PCIe, and you don't know how long will it take to actually receive it back. So like I mentioned on the previous talk, the optimistic way is that it will happen in between our system clock reads if we don't have any hardware acceleration. It never happens like that. If you try to compare the clocks, like because Intel recently implemented in their platform CGPIOs, which are the things that can output the TPS signal based on the hardware clock of the CPU. If you put the TPS output of both systems, like from your network card and from your CPU, and try to capture them, there will be always an offset of around even 1 microsecond. So your notion of time based on this fallback is at best around 1 microsecond apart. That's why we have the PTM. We are implementing the PTM in our devices, both Intel and NVIDIA. And this actually is based on the hardware, like or like PCIe way of time stamping. So there is a special transaction on a PCIe bus that allows you to timestamp the transaction and know how long this transaction takes on a PCIe bus, and then correct for that. And once you implement that in your device, this shift between the CGPIO time and your device time gets to a couple, maybe tenths or maybe to the hundredth of a nanosecond.
This might be a silly question. It seems like why can't you keep the system clock synced to NTP and then be able to translate between
NTP is milliseconds apart. So it's like 3 orders of magnitude worse than PTP.
Kind of two things. One, I can answer your question. You can't just sync between, like have NTP sync, because the clock source for the device is fundamentally from a different clock source than the clock source from the platform. So if those are out of sync or out of phase, and you're trying to compare them, you can't just do like a math comparison because they're not fundamentally the same source. Question for you though, you mentioned for the transmit and receive timestamps to make it better, you would capture one timestamp and translate both for each clock. One thing I was curious about is in a real hardware, there is physical transmit delay or delay when you transmit and then actually send over the wire. So there would be real path delay between 2 points.
We can emulate this by just adding a static offset to the receipt. It's more about getting it consistent, the offset, rather than getting it all like over the place if we just rely on kernel not doing anything.
In real hardware, you'd want to be capturing as close to the same point transmit or receive flow. Makes sense. Okay.
Hi. Question about Netdevsim. So have you tried linking one Netdevsim with a real device?
Does that work? Not possible. It's because it's only allows you to connect the device, like the Netdevsim device, to another Netdev, not a connection to another Netdev, only to another Netdevsim.
Is that like fundamentally impossible, or is that something that you could do?
I mean, for timestamping, it wouldn't make much sense because it would be done on a software layer, and then you will not have a hardware timestamp because hardware timestamp requires the packet to go through the pipeline of hardware.
Right.
Because the device captures it on the very end of the pipelines usually and tries to somehow, get it as close to the wire as possible. So
the reason I'm asking is because it would be nice if, let's say that I'm implementing a new piece of hardware and I want to add support for PTP. So like, could I link a Netdevsim with my device or driver in question and know and Netdevsim is well implemented, like and then run these and check that my implementation is correct as a secondary device, and then you sort them out, and then you can also test it as the primary device. Is that something that could be done?
So unfortunately, I don't really see a path to make it happen unless so I think Netdevsim cannot transmit anything to another device, because the problem is still the pipeline. So it will still need to wire out something somehow so that the other side can actually use. And in that case, you would better probably be with just getting some well-known device that actually does the timestamping well and connecting it to your device.
For developer, I would recommend you to take through the Netdevsim implementation in PTP to see what is required for fully functional support.
Yeah.
And then use the PHC control application to see if the connection to PTP the PHC is correct.
I see.
Yeah.
And then what about going the other way? Because for Netdevsim, you have a PHC mock.
Yes.
So what if I'm someone who's building like hardware support, like whatever the hardware equivalent of PHC mock is, then I can use Netdevsim and then use a bunch of self-tests to verify that my hardware implementation is correct. Is it something that's possible to do?
It might be challenging, especially when it comes to timestamping, right?
Yeah, because the problem is you need the same source for the timestamps.
Yeah, the timestamps and the
clock.
Yeah. We need to have the connection to PHC and something that generates your timestamp.
Okay.
Yeah, but PHCCTL is usually good enough to test the implementation of the PTP hardware clock part of the driver.
There are no other questions. I actually had a suggestion and I just wanted to run it by you guys. So Milena, myself, and a few others at Intel, we were talking about, we have like a time-focused working group, which is probably longer because there are too many time-related features in the modern NICs, and we need to expand the scope beyond just PTP. So what does everybody think about it? And maybe we can discuss the scope over the mailing list. Something like, of course, PTP, then there is Syncy, there is time-based scheduling features like EDT. There is also completion timestamps and a whole bunch of other things might be related to telemetry or, latency delays and things like that. So the scope is becoming very big. As far as we see, modern NICs have way too many time-related features. So I think it would. Yeah, I mean,
I believe we may know more about it after the workshop that Dave will host, or I will also come with some PTP topics. I believe there are other as well, and then we will see how big is the scope and how big is the gap, and then we will be able to.
sorry, maybe I missed your workshop. Is it time related?
No, it's not. It's. But we will snatch it and make it PTP. We will definitely counterbalance it.
Yeah,
No
no,
more.
I think, yes. So maybe we can have some little bit of that discussion, but I think just time-related workshop is what we need to. If we need to have an ongoing working group, that's also a possibility. But yes, at the conference for sure, maybe half a day or a full day. I don't know. Yeah.
I'm realistic. I don't believe we will close everything at this conference. So.
Yeah. Okay.
I was just saying thank you for working on it, and I'd like to see this get moved. I think it's important to always software views of what we're capable of. Is that?
Yep.
Thank you.
Thank you. And enjoy the rest of the conference.